if alpha is an element in K, K is contained in F, K is an extension of F, then consider the map phi alpha from Ft to K such that it sends a map Ft to F of alpha. Then the kernel of phi alpha is if it's 0, right? It can either be 0 or it can be non-zero. If it's 0, then we say alpha is transcendental over F, okay? And if it's non-zero, then since F is a field, so F of t is a PID, that polynomial rings over a field is a PID. So then what can I have? There exists some monic irreducible polynomial Pt such that kernel of phi alpha is generated by Pt. And what does this typically mean? Therefore, P of alpha is 0, and if Qt is in Ft such that Q of alpha is 0, then P must divide Qt. Pt must divide Qt, right? So, in other words, therefore, alpha is algebraic over F. Alpha is algebraic over F. Moreover, what more we have by the first isomorphism theorem? So, by the first isomorphism theorem, what do I have? Ft mod Pt is isomorphic to F alpha, which I had generated as, defined as the collection of all elements of this form, right? An alpha to the power n such that n is some natural number and each ai comes from F. So these are the collection of all just evaluated polynomials at alpha, right? And then what we did recall, then we had proved that since this is a subring of K was a field, so it's at least an integral domain. If it's an integral domain, then this is a prime ideal, right? Which implies that Pt is prime element, right? Which implies that Pt is irreducible, right? Which implies that the ideal generated by P is maximal. In fact, it directly follows from here itself, because Pt is a non-zero prime ideal in a PID. Every non-zero prime ideal in a PID is a maximal ideal, so it is evidently a maximal ideal, which implies that Ft over Pt, this is a field, right? And what is the field? So it is basically isomorphic to this, so this is the field, right? Now what more had we said? We had said that, so we had defined this to be the, if you recall, we had defined this to be the smallest subfield of K containing, recall, smallest subfield of K containing F and alpha, right? Therefore, since it contains every element of F and alpha, therefore all the elements of the form A0 plus A1 alpha and so on till A n alpha to the power n belongs to F alpha by the properties of fields, right? Is it clear? In other words, this field is contained in F alpha, but F is contained in F alpha, right, as the set of constant polynomials evaluated at alpha, and alpha itself is contained in F alpha, since alpha can be thought of as the evaluation of alpha where f of x is x, right? So that implies, now this is the smallest field containing both f and alpha, and this is a field, so that implies that f of alpha is also contained in F alpha, right? So that proves that the smallest subfield containing alpha, it actually assumes the form of elements A0 plus A1 alpha and so on till A n alpha to the power n, where n is some natural number and each ai comes from F. Then what we had proved, then we had proved, okay, and we had also said that this Pt, the polynomial which generates the kernel, this is called the minimal polynomial of alpha over F, right? And then we had proved that F alpha over F, the degree of this extension, is exactly equal to the degree of Pt. That Pt is the degree F of Pt, whatever you want to denote it as. This is the minimal polynomial of alpha over F. And how had we proved it? So the proof was fairly simple. What we had done, that if Gt is an element, we did it in this way. If Gt is an element of F of t, right, such that the degree of G is greater than degree of P, then I can divide G by P, implies that there exists Qt, Rt in Ft, such that I can write Gt as Pt times Qt plus Rt, right, using the notion of unique factorization domain or Euclidean domain, whatever you feel like talking about. What is the extra condition? The extra condition was the degree of R was less than the degree of P, right? Then what would we have? Then clearly observe that. What can I conclude from here? So GT is equals to RT in FT mod PT, right? What does this mean? This means that G at alpha must be equals to R at alpha. Therefore, what do I conclude? That if G of alpha is an element of F alpha, then G of alpha should be of the, so what should be the form of R of alpha? It should be of the form A0 plus A1 alpha, so on and so forth till An minus 1 alpha to the power n minus 1, right? Where degree of P is equal to n, right? Because the structure of the R as a polynomial, it can be easily observed from here. So in other words, what do I have? That 1 alpha till alpha to the power n minus 1. So this spans F alpha, right? And carefully observe that there are n elements. And you can also prove that this is linearly independent. And why is it linearly independent? If you carefully observe that if you take a linear combination, say A0 plus A1 alpha and so on till An alpha to the power n minus 1, n minus 1 alpha to the power n minus 1 and take it to be 0, then that means that if I choose this polynomial, say h of t equal to A0 plus A1t, so on and so forth till An minus 1 t to the power n minus 1, then this polynomial is such that h of alpha is 0, right? Which is a sheer contradiction as p of t does not divide h of t. But since p is the minimal polynomial of alpha over f, every polynomial which takes alpha as a root must be divisible by p of t. So this is a contradiction. Therefore, each and every a0 must be, each and every ai must be 0. So it is linearly independent. So what does we prove? So we prove that f alpha over f, right? This contains the basis to n minus 1, and therefore its dimension should be, so its dimension of f of alpha over f, this should be n, and n was the degree of the minimal polynomial pt, right? Now I think it's clear. Okay, fine. Right now, okay, now let's come back to our discussion. So in the previous lecture we had introduced the notion of an algebraic extension, if you recall, right? So we had said that k over f is algebraic if every element of k is algebraic over f, That means for every element there exists some polynomial over f which takes that element as a root, right? And in the previous lecture we had also proved that a finite extension is algebraic, if you recall, right? And the proof was very simple. Just go back to the previous lecture. I guess in that part there was no lag. Please go and view. But here we prove something a bit more general. Okay, let E over F be an extension if if this is finite, okay, then E is algebraic. This is something which we have already proved, and finitely generated over F. That is, it is extended by some finite number of elements. Clear? It is finitely generated over F. Conversely, if E is generated over F by a finite set of algebraic elements, then it is of finite degree. Okay, so in the previous lecture I had said that the converse is not immediately true, but I think I haven't said this in the previous lecture. A certain type of the converse is true. So what are we proving here is that if E is finite, if the degree of E over F is finite, then it's algebraic. This is something which we have already dealt with in the previous lecture. No need of proving that anymore, but it's finitely generated as well. Let's try and prove this. Okay, suppose E is exactly equal to F, right? Then what do we have? Then E is F with the empty set, generated by the empty set, right? So it's quite tautological in some sense. Okay, let me set the notation first. I think I haven't discussed about this. Okay, this is referred to as F as A1, A2 and so on, where A is this set. Okay, let's come back. Yeah, so fine. So therefore let E be not equal to F. Then this implies there exists some element alpha 1 which belongs to E minus F. Okay, then if E is equals to F generated with alpha 1, we are done. Okay, else let E be not equal to alpha 1, f generated with respect to alpha 1, then choose alpha 2 contained in E minus f generated by alpha 1. Clear? Okay. Then if E is equals to f alpha 1 alpha 2, which is f alpha 1 alpha 2, then we are done. Else continue the process. Else continue the process. Okay. Now observe what happens. So now the question arises is that does this process ends finitely? If this process does not end finitely, then we cannot say anything. But if this process ends finitely, since each of these extensions are finite in nature, right? Because we have already proven that E is algebraic. So each of these elements alpha 1, alpha 2 are all algebraic over F. Therefore, the degree of f alpha 1 over f is finite. F alpha 1 alpha 2 over f, this can be written as, in some sense, f alpha 1 alpha 2 over f alpha 1 times f alpha 1 over f, right? So this is also finite, this is a finite extension also, and this is also a finite extension, right? Clear? Because why is it this a finite extension? Because since I have chosen alpha 2 outside f alpha 1, so the minimal polynomial of alpha 2 over f is also the minimal polynomial of alpha 2, or at least there is some polynomial whose root is alpha 2, some polynomial of finite degree whose root is alpha 2, which is in f, that is also a polynomial in f alpha 1, right? Because alpha 2 is not in f alpha 1, right? Clear, right? So each of these are finite extensions, right? So therefore now observe, now f alpha 1, this has less degree than f alpha 1 alpha 2, sorry, over f, and these are all less in degrees than ef, right? And this is finite, right? Therefore the above process must end finitely, must end finitely, and therefore E must be f generated with respect to some finite number of elements, which implies E is finitely generated over f. Okay, is it clear? Clear, fine. What can we say about the converse? Conversely, suppose E is generated by some finite number of algebraic elements, as we had claimed in the hypothesis. Okay, so where each alpha 1 alpha 2 till alpha n are algebraic over f. Okay, then f alpha 1 over f, this is finite because alpha 1 is algebraic over f, right? Therefore f alpha 1 alpha 2 over f alpha 1 is also finite by the same argument. So what do I actually have? So I have something of this form, right? So E is equals to f alpha 1 till f alpha n is an extension of f alpha 1 to f alpha n minus 1, so on and so forth, right, till f alpha 1 over f over f. Is it clear? So I can write E over f as, I mean the degree of E over f as alpha 1 till alpha n over alpha 1 to alpha n minus 1, then alpha 1 to alpha n minus 1 over alpha 1 to alpha n minus 2, and this process continues till f alpha 1 over f. And all these are finite in nature, and there are finite number of elements, all of these are of finite value, so this must be finite. Therefore E over f is a finite extension. Is it clear? Is it clear? Now see the following, that is, suppose, observation, suppose let us say L over E over F is a tower of field extension. These are called tower of extensions. Okay, so the tower of field extensions such that, let us say L over E is algebraic, E over F is algebraic. Clear? Is it clear? Then every alpha in L is root of a monic polynomial over E, right? It's a monic polynomial let's say x to the power m plus am minus 1, x to the power m minus 1, so on and so forth till a0 in et or ex, sorry, right? Now observe the following. This is a very trivial observation. Now the field generated by a0 till a m minus 1 over f is finite over f. Why is it so? Each of these ai's are coming from E, as each ai comes from E, right? Hence are algebraic over f, because E over f is given to be an algebraic extension, is algebraic over f. Clear? Therefore a finitely generated extension with respect to algebraic elements is algebraic. We have just proved. Therefore f from a0 to m minus 1 is algebraic over f, is algebraic. Is it clear? This implies that if I add the element a minus 1 with alpha is finite, right? Actually what we have proved that this is finite. We had proved, actually, let's go back, we have proved that this is actually finite. Okay, an extension by a finite number of algebraic elements is actually finite. So this is finite, this extension is finite, therefore this extension is also finite. Okay, right? And it is exactly infinite over f. Why is it so? Just by the theorem which we have proved previously, that is the degree of L over f is same as the degree of L over E times the degree of E over f, right? As degree, so if I take this over f, then this is basically f from a0 to am minus 1 alpha as an extension over a0 to am minus 1, right, times f from a0 to n minus 1 over f. Now this is finite and this is also finite. Why is it finite? Because alpha is algebraic over E. So alpha is algebraic over the field extended by a0 till an minus 1, because each of these ai's are in E, right? Pretty obvious to notice this. And alpha has a polynomial over E. So these, both of these are finite, therefore this is finite. So if this extension is finite, what do we conclude? So this implies that f a0 to m minus 1 alpha over f is algebraic, right? And clearly alpha is an element of this extension, right? That implies alpha is algebraic over f, right? And alpha was an arbitrary element chosen from L, right? So this was arbitrary in L, which implies L over f is an algebraic extension. Is it clear? Got it? Fine. So now there is one more observation which I should have given in the previous lecture, but I somehow forgot, is the following. See, we had proved this, or rather let's discuss it here itself, because I have already repeated the extension generated by an element in this lecture itself. So let's prove this, or rather observe this. So another observation, and most of these observations are actually theorems in the standard books, but I prefer saying them as observations because actually these are the things which we are observing while analyzing these concepts, right? And before being developed as theorems, they were actually observations. After observing such things, they have been formulated as theorems. Rather, observe that suppose alpha is an element in K, K is a field extension over F. Then K over F alpha over F is a tower of extension. Is a tower of extension. But then what does it conclude? It concludes that, okay, so suppose I assume that K over F is, okay, so actually there is a inbuilt assumption here which I have missed, that since I am talking about F alpha, so let K over F be finite. Hence it's algebraic, so alpha is algebraic over F, right? That's what, so therefore I can talk about this in a well defined way. Now, now see the following. So what does this conclude? This concludes that K over F can be written as K over F alpha degree times F alpha over F. So this, what does this mean? This means that the degree of F alpha over F, this divides the degree of K over F, right? Right? Now see this. Now suppose K over F is prime, okay, then F alpha divides F, I mean sorry, what I am saying, divides K over F, the degree of K over F implies that the degree of F of alpha over F, this is either, suppose this is prime P, so it's either P or 1, right? But there was a exercise I had given in the previous lecture, I hope you guys have done it. that I am giving this here as well, that if K over field is an extension such that this degree is 1, or rather then this degree is 1 if and only if K is equals to F. See, if this degree is 1, then what does it conclude? Just go via the vector space procedure in this case, and the converse is quite trivial. Okay, it's a very easy observation, you can do it on your own. So if F alpha over F is 1, what does that conclude? Okay, so if F alpha over F is 1, then that concludes that alpha is in F, but that's a contradiction. I said that alpha is in K, right? So I hadn't mentioned it, right? So alpha is not here. There's no way of talking about alpha in F, then what is the use of analyzing the field generated by alpha? Getting my point? So alpha is not in F, okay, and then we are doing this observation, right? So that's a contradiction. So F alpha over F is a prime, right? But does that conclude anything? Carefully observe, right? So this must be, that implies that this is exactly equal to K over F, right? What does that mean? That typically means clearly that F of alpha must exactly equal to K, right? Because both of them are having same dimension, and F of alpha is as a vector space is a subspace of K. Both are vector spaces over F having the same dimension. So F of alpha at least as a vector space must be equal to K, and since it is already a subfield of K, so it must be exactly equal to K. Clear? Actually, throughout field theory, two concepts go side by side. We need to analyze our concepts in terms of fields as well as in terms of vector spaces as we require. Getting my point? Therefore, what do I conclude that? So what I typically conclude from here is the following observation, that is, if K over F is prime, alpha is in K minus F, then F alpha must be equals to K. So this is given as a theorem in most books. Is it clear? Is it clear to everyone? Fine. Okay, yeah, fine. Right. Okay. Now we move on to another very important notion, what we call algebraic closures. Algebraic closures. Okay. So let's start up with this. And okay, so let's again start with some observations. Okay. Suppose K over F is a field extension. Okay, K over F is a field extension, and let's say E is the collection of all the elements alpha in K such that alpha is algebraic over F. In other words, F is also contained inside E, right? Because every element of F will be algebraic over itself. Right. So now observe the following. Let alpha and beta be in E. Okay. Then what does that mean? That means that the extension generated by both alpha and beta over F, right, that can be written as F of alpha beta over, let's say, F beta multiplied by F of beta over F, right? Is it clear? But now see, this is a very trivial observation, that is, see, alpha and beta taken from E, so they both of them are algebraic over F, right? Now let's say PT is the minimal polynomial of alpha over F and Qt is the minimal polynomial of alpha over F beta. Okay, but if Qt is a minimal polynomial, or rather if Pt is the minimal polynomial alpha over F, then what does that mean? That means, so this means that Pt is also in F beta and Qt is the minimal polynomial of alpha over F. What does that mean? Right? Can't I say that Qt divides Pt? Right? Clearly, because the minimal polynomial is the least possible polynomial, least monic irreducible polynomial. So if Pt is a polynomial over F which admits alpha as a root, so Pt is also a polynomial in F beta having alpha as a root, and Qt is the minimal polynomial of alpha over F beta. So Qt must divide Pt in F beta. In any way, this extension must be less, right? The degree of this extension must be less. That is, the degree of F alpha beta over F beta, this must be less than the degree of extension of alpha over F. Got it? So therefore, what do I have? Therefore, F alpha beta over f, this is less than or equal to, the minimal polynomials can be same also, over f times f beta over f. Now since alpha and beta both are algebraic over f, so this is finite integer. Is it clear for everyone? Right? But since it's finite, what do we have? This means that f alpha beta over f is algebraic. That means every element in this field f alpha beta must be algebraic over f. And if you observe carefully, this is a field, alpha beta are in f alpha beta. What does that mean? That means alpha plus beta, alpha beta, alpha inverse, if alpha is non-zero obviously, are all algebraic over f. Hence must be inside E. What do we conclude from here? Therefore E is actually a field. Isn't it that? In fact, it's a field contained in K containing F. Isn't it that? Therefore, the collection of all algebraic elements over some field is a field itself. In fact, it's a subfield over the field extension. So, what do we actually conclude from here? Let me summarize. Summarizing, we have the following theorem. Let K over F be any field extension. Define T as the collection of all elements alpha in K such that alpha is algebraic over F. Okay. Then E is a subfield of K containing F. Isn't it that? Now observe this very carefully. So if I consider now C, or rather let me do it in this way. So if I consider C as a field extension over Q, and let's say I define, let's say, Q naught to be the collection of all alpha in C, or rather let me define it in a literal sense, Q naught be the set of all algebraic numbers, right, that are complex numbers which are algebraic over Q. Getting my point? So what can I say from here? Then Q naught must be a subfield of C. Then C over Q naught over Q is a tower of extension, right? Is a tower of extension. Is it clear for everyone? Right? Clear. Okay. Now recall one thing more. We had proved it in the first lecture itself that the number of algebraic numbers is countable. Also, Q naught, this is countable, right? We have proved it that there is a finite to one set from the collection of all algebraic numbers to the polynomials over Q. The polynomials over Q are in some sense isomorphic to n tuples of Q, so it must be countable since K is countable, and due to this existence of a finite to one map, this collection of algebraic numbers must be countable. Is it clear? Now observe something very interesting. Okay. If I choose any polynomial ft in Qt, okay, then all roots of ft is in Q naught, right? Because every algebraic element over Q, that is every algebraic number must be in Q naught. Every such algebraic number is actually the root of some polynomial. So if I choose any polynomial over Q, the roots of those are algebraic numbers, so those must be in Q naught. So what does that mean? That means that this implies ft splits into linear factors, that is, it is factorized into linear factors over Q naught. Every polynomial over Q splits into linear factors over Q naught. This brings us to the following definition, a very, very important definition. If you want to pursue a career in algebraic number theory, then this is sort of the base point from where you start studying it, okay? Because there you need to talk about algebraic number fields and norms and traces of fields, so on and so forth. And there the typical concept to start with is the notion of an algebraically closed field, okay? Finite extensions over Q, fine? Right. Finite extensions over Q are some sort of called the number fields, okay? Yeah. So as I was saying, that is sort of the the starting point, in some sense the starting point of algebraic number theory, okay? Getting my point? Fine. Okay, yeah. Okay. Yeah, okay, so let's come back to what we were trying to discuss. Okay, so this brings us to the following definition. That is what I said. So a field F is said to be algebraically closed. Algebraically closed if every polynomial in Ft, that is over F, is a product of linear factors in Ft. In other words, all the elements which are algebraic over F must be inside F. That is, all the elements algebraic over F must be in F. Right? So here you can relate in some sense to the notion of it being algebraically closed. Right? Every algebraic element over F must be inside F. Is it clear to observe it? Okay. In other words, every non-constant polynomial must have a root in F. Is it clear? Right? Okay. Now observe the following. It's actually a very important observation. In the next lecture, I won't prove it in the next in this lecture itself because it's already a bit long. In the next lecture, we will be in some sense trying to prove that every field admits an algebraic closure. Okay, so this is the content of the next lecture. Content of next lecture, that every field admits an algebraic closure. Okay, fine. But now we prove something very interesting. That is what we call a well-known theorem of algebra as well as analysis, is the fundamental theorem of algebra. This is, as I say, that this is also one of the very important theorems we try and prove in analysis, specifically in complex analysis. Right? That is, what does it say? That C, or in some sense, that every complex polynomial has all its roots. Right? Is it clear? Roots in C in some sense, right? But what does this theorem typically mean? This means that C is algebraically closed, isn't it that? C is algebraically closed. Getting my point? Right. Now there is a very interesting proof in complex analysis where we do the following. So if I choose Ft as some polynomial over C, then now it's a polynomial, so it's analytic, or rather it's holomorphic. It's holomorphic over C. So I'm just giving a brief. So this means that F is holomorphic over C, that is entire. Okay, suppose f of z is non-zero for every z in C. So what I can do is that I can define g of z to be 1 by f of z. So it is in some sense like this: a naught plus a1z and so on and so forth till a n z to the power n. Bring z to the power n common outside, so it becomes a naught over z to the power n plus a1 by z to the power n minus 1 and so on and so forth till I have here a n. Right? Now as mod z tends to infinity, this goes to 0, this goes to 0, right? So and so this is in some sense bounded, right? And this goes to infinity, so this goes to 0. So that means, and now since f is entire, g of z is also entire by the definition or the properties of entire functions. So therefore what does it mean? This means that g of z is a bounded entire function. I am not giving the proof, I am just giving a scratch work. Therefore by Liouville's theorem, g of z is constant, right? So have I chosen it to be not every complex polynomial, I am sorry, every non-constant complex polynomial. Okay, right? See, this is the fun thing about proofs and the fun thing about my lectures, because I don't make them, to be very specific node based, because while even if I write something wrong in the theorem, while trying and proving it out, I come up with whatever I have written wrong, right? So let's go back. So by Liouville's gz is a constant, but that means that f of z is a constant, hence a contradiction. Got it? Therefore there must exist at least one element such that f of z is 0. Got it? And hence inductively I can continue doing it throughout the degree of the polynomial, right? So if it admits one root, what I am trying to say is the following. This is sort of clear, right? What I wanted to say is sort of clear. So now if I write f of z, and let's say z minus z naught times g of z, then I can apply the same to g of z. then it will be reduced to, say, suppose z minus z naught into z minus z1 times sum h of z, applying again to h of z and continuing this throughout. This process ends finitely because the degree is finite and the degree is constantly decreasing, right? So ultimately we will get that f will split into linear factors. So this is the analytic proof of C being algebraically closed. So this is the analytic proof of C being algebraically closed. Mathematics is unified, as we have proved now. We have a proof in terms of analysis, and now we are going to prove it algebraically. Okay? Okay. Fine. Let's see. Now see, proving C is algebraically closed is equivalent to proving that Q naught is algebraically closed, because Q naught is contained inside C. So if Q naught is algebraically closed, C is automatically algebraically closed. Getting my point? No, actually I do not mean to say that. I mean, see, typically for C being algebraically closed, I need to take hold of complex polynomials. But what we are concerned about are rational polynomials. Okay, getting my point? Okay. So what we prove is the following. Okay, consider. So I got a bit confused. I'm sorry. Just forget whatever I said just now. Okay. When I'm making these lectures, it's very hot and humid here because I need to keep my fan off and make this lecture. So please pardon if I say something wrong, because that's just a slip of my tongue. Sorry. So consider C over Q closure over Q, because every element in C will automatically. What I mean to say is the following. See, what I said was actually right, but I didn't mean it in the right way. If an element I choose from C, right, it's automatically algebraic over C. There's nothing to prove. What I mean to talk about is being algebraic over Q. That will make some sense. So if I try and talk about an element being algebraic over Q, then I can actually prove that Q naught, our symbol Q naught, this is algebraically closed. That will suffice, right? Right? That is what I am trying to say. Because if I choose an element out from C, then it is automatically algebraic over C. That the analytic proof immediately gives us, right? And we have already proved that if I choose an element from C and I consider C as an extension over C, so that element is automatically algebraic over C. So there is nothing to talk about complex polynomials. What we can talk about is rational polynomials. But as we talk about rational polynomials, it suffices to prove that Q naught, that is the algebraic closure of Q, is algebraically closed. Clear? Okay. Okay. So I think I haven't defined the term algebraic closure yet of now, or did I do it? Have I done it? I use the notion of being algebraically closed. I haven't used the term algebraic closure yet of now, but I am keep repeating that Q naught is the algebraic closure of Q, Q naught is the algebraic closure of Q. I'm so sorry, I should have mentioned it previously. So let me just define it for now. I would have defined it in the previous lecture. So a field extension K over F is called an algebraic closure. So K is basically called an algebraic closure over F if A, K is an algebraic extension of F, and B, K is algebraically closed. Okay, is it clear? So we are trying to prove the same thing, that Q naught is algebraically closed. That is something we want to prove. So it is in some sense wrong for me to use the term algebraic closure because we haven't proved it yet that it is algebraically closed, right? But it's an algebraic extension. That is something which you can very trivially observe, right? Right? Because if I choose an element alpha from Q naught, then that is a root of some polynomial by definition, because these are the collection of all algebraic elements over Q. So this must be an algebraic extension. That's quite trivial, right? And if I prove that it's algebraically closed, then I will automatically prove that Q naught is an algebraic closure. So yeah, so I have been using the term for a long time, I guess, but that is what I meant actually. So what I actually meant is that it's an algebraic extension over Q, and it's every polynomial over Q splits over Q naught. Okay, fine. Let's prove it. So left f of t. So I need to prove it that it's algebraically closed. So for it to be proven algebraically closed, what I need to prove is that if I choose a polynomial from Q naught t, then I need to show that it splits into linear factors over it, right? So then let f of t be a naught plus a1t, so on and so forth till a n t to the power n. Okay. Now let alpha in C be a root of ft. Okay. Clear? Why do we know about the existence of such roots? Since C is algebraically closed, which we have proved analytically, right? Since alpha is since C is algebraically closed, there exists a root alpha of ft, right? Then observe, then alpha is algebraic over the extension of q by a0 till a, right? Clearly observable. Then again we have the same situation of having a tower of extensions, because then I have the following tower: alpha a0 till an over q extended using a0 till an over q, right? The degree of f is n, so this extension must be of degree less than n, and this is again finite. Why? Because each of these ai's are finite over q, because those have been chosen from q naught. Those coefficients are these are the coefficients of ft, and the polynomial is over q naught. So therefore each of these elements are over q naught. So they are basically algebraic in nature over or other algebraic numbers. So what does this mean? This means that alpha a naught till an over q is finite, hence algebraic. This means alpha is algebraic over q, which means that alpha is in q naught, and alpha was an arbitrary root of ft. So what does that mean? Therefore, since alpha was an arbitrary root of ft, what does that mean? Therefore, every root of ft is in q naught, which implies that ft splits into linear factors over q naught. Again, ft was an arbitrarily chosen polynomial over q naught, which means that q naught is algebraically closed. Clear? Got it? Okay, right. So let this element let this lecture be up till this much. In the next lecture we'll talk about algebraic closures in more details, and to prove that every field admits an algebraic closure, we need to make use of something set theoretic, which is actually very famous, known as the Zorn's lemma. Okay, and then what we will do is so in the next lecture we also need one more thing, that is uniqueness of field extensions. That is also something which we need to talk about in the next lecture, because we need to prove uniqueness of certain field extensions. For example, we will prove uniqueness of algebraic extensions, typically algebraic closures. Actually, we will prove uniqueness of algebraic closures, and then we will be when we will be formally introducing the notion of splitting fields, we also need to introduce the notion of the splitting fields being unique in nature. Getting my point? Okay, so meet you guys in the next lecture.